remember kind of how we were doing that yesterday. Basically, whatever your endpoints were. Then I want to show all of this work. -8 to 12 we got. So 12, 8. And then we just want to say add each of these x values now. Like what we talked about yesterday is since all of the values in this interval satisfy our ratio test values, we know any value in there is going to work. So if I plug in a 10, a -4, if I plug any of those values into this, it's going to create a convergent series. But what happens is at the endpoints is when our ratio test would give us a 1, it's when it equals 1, and then that's inconclusive. So that's why we just need to do a little more work to determine what happens at these values. So if I took this -8 and I plug it in, that's going to give me a -10 to the nth power, and then all over 10 to the nth. So sometimes people get a little confused with this. You can just do a -10 divided by 10 if they're both raised to the same exponent. So this does just become a -1 to the nth power. Strongly suggest trying to simplify these as much as possible. Once we see this now just tells us this is one that's going to bounce back and forth between 1, -1, 1, -1, 1, -1. So in terms of this converging, there's no way that can converge because our very first option, which is the nth term test, this limit wouldn't exist because you're just bouncing back and forth between two different values. So we'd say this diverges, nth term test. The limit as n goes to infinity does not exist. So then the other one is the 12 to determine if this guy's going to work. So take your 12 and plug it in. That would give you a 10, positive 10 now to the n, over a 10 to the n. Well, that's just going to be the exact same value divided by itself. So that limit's going to, or that term's going to simplify to be a 1. For the exact same reason, in terms of almost the exact same reason, I should say the exact same test. So this still diverges because of the nth term test. The reasoning is slightly different in terms of our words and what we're going to put down. That is because in this case, the nth term test, the limit as n went to infinity was the 1 and not the 0 that we need to be. So we don't close either one of these off. That's your interval. Did we do the radius of this one yesterday? We talked about that, right, too? All right, so our radius of convergence, we talk about how far left and right we go is 2. All right, so that's the endpoints. So let's do 6. Let's kind of start one from the beginning, see if we remember how we got through all of that. So what we're ultimately trying to figure out is what values of x would make this series converge. And the way we go about that is with finding the ratio test. So doing the n+1 series. And then dividing that, dividing by, also put parentheses. Did I have parentheses around yours? Did I add that in there? Okay, there should be parentheses around those. I want the whole thing to that power. And then divide that by the original. And then we want the absolute value of that so we can get to the left and to the right of the interval. Well, the 2x to the n's will cancel. So all we should be left with from that is the 2x. First time we did this yesterday, people kind of looked at this, weren't real sure. The second time, I think we understood that as n goes to infinity, if all we have is a 2x, there are no n's. So this really kind of acts like a constant. So this would just remain that 2x. So that's kind of like when we do the ratio test, you get to the end, that's your p value right now. So you don't necessarily need to write this down, but that's our p. But it's a variable expression. So there's multiple answers to this. What we know is when we do the ratio test, as long as our p value is less than a 1, we're good. So that's why we take that, set it less than a 1. That then gives us the inequality that we're either less than 1 or greater than a -1. And then divide by 2 everywhere. Let's first identify our radius right now. If we go back up to this, notice how there was no horizontal shifts in this at all. So that means you're centered at 0. And if I go right a half and then left a half from 0, this is another one where our radius is not just a regular old 1. Your radius here is a 1/2. You go right 1/2, left 1/2 from the 0. All right, so then from there, we need to plug in each endpoint. So we'll say at the first endpoint, the negative 1/2. If you plug in a negative 1/2 into here, you're going to get a negative 1 to the n. We just did that in the previous problem, right? That diverges. Limit doesn't exist, so that one we know will not work. And term test. When we plug in the positive 1/2, again, we basically reproduce the previous problem. Because now don't you just get the 1 over n again, so the limit's a 1. So you basically just recopy down the, I might actually do that just to save us a little bit of time, because the same thing would have happened here that it happened over here. Diverged, and term test. Your limit was a 1, not the 0 that was supposed to be. Okay. Okay, let's go to the back page. Yeah, these all get a little adventurous in the back. Yeah, and 9 and 11 are the big ones too. So 7. Do I want to do 7? Yeah, I want you to do 7. Go through the ratio test here. That part we should be able to kind of get a handle on. Don't necessarily worry. Well, let's go ahead. Go ahead and do the negative now. I think I told you to cross it out the first time. Let's now deal with that negative. So we're going to do negative 1 to the n plus a 1, x plus 2 to the n plus a 1 over an n plus a 1, and then multiply by the reciprocal. All right, then the negative 1 to the n's should cancel, and the x plus 2 to the n's should cancel. So what we would initially have, we still have the little negative 1 there. We have an x plus a 2 to the first power, and then the n. And then on the bottom, all we would have is an n plus a 1. I'll tell you how you want to handle this, but we can just take the absolute value of that negative 1. It's going to make the solving and setting up the inequalities much, much easier. So we're going to say that we took the absolute value of that single negative 1. We're not going to deal with that because it just kind of gets even uglier inequality to deal with. So find your limit. So as n goes to infinity, the n's have powers of 1. So you're just going to look at your coefficients. The numerator had a coefficient of x plus 2, the denominator a 1. So that's our limit. And we know if it's less than a 1, we are good. Set up your inequality then. Solve that. And we know then that between a negative 3 and a negative 1, any value is going to work. All right, I'm going to give you a minute. Try the endpoints here, because now a little bit different. See if we can figure out what these endpoints tell us happened. I have a little number sense here to think this through. Could test some old algebra stuff. If it does converge, then we're going to close it. If it doesn't, we leave it open. Let's see what we got. So when we take the -3 and we plug it in here, you would have had the -1 to the n, that's this one, and then a -3 plus 2 gives you a -1 to the n again. So just understand what that would mean. Do some algebra here and clean this up. If I have like terms multiplied together, can I multiply those together? What do we do with the exponents? Add them. So n plus n is just a 2n, all divided by n. So now think about what that would mean. If I throw in a 0, wouldn't I get a -1 to the 0 power? So that nothing really happens there. Let's say it's a 1. Wouldn't I get a -1 squared? Then I plug in a 2, I'm going to get a -1 to the 4th power. A 3 gives me a -1 to the 6th power. What is this always spitting out? Good question, Lily, or Amy? Okay, what do you think? Good. What we really have created when we completely simplify this is a 1 over an n. That's why we would then, or she said that this has to diverge because it's really just a harmonic series. So it obviously isn't obvious right away, but at that x value of a -3, we create the harmonic series, so it's going to diverge. We leave that one open. When we go to the next one now, you could multiply these together, that's fine. So because they have the same exponent, it does work that way. But isn't 1 to the n really just a 1? So we could just say that that's just going to go away. It's a 1. And all you're really left with then is a -1 now to the n over an n. That now does what? Good. Converges conditionally because that's the alternating harmonic series. So this one we would say converges conditionally, and then we will get the alternating harmonic. So that happened at the x value of a -1. We come down here, we close that one off, then this is our final answer. If I ask you for the radius, notice how we went from a -1 to -3. Since this was an x plus a 2, we started at -2. So then we just went 1 left and right, so our radius is just 1. All right. All right, where are we at here? 8. I might leave you 8. Yeah, let me leave you 8. I definitely want to do 9, 10, and 11, and I don't want to fall behind too much. So you should get, if you wanted to try this guy, what do we got? 0, closed, and then 2 gets left open if you wanted to try that one at some point. The next one's a big one. All right, so go to number 9. Now we introduce some factorials, so those are always fun. So go ahead, set up your ratio test first of all. Make sure we got that part of it down. All right, and just keep in mind, the n plus 1 is first priority, so you're going to do that first. Then you multiply by 2. Then you're going to add that one. So we would get x to the 2n plus a 3. All right, and hopefully we know that n plus 1 factorial, we're just going to take down to where we get just the single n with a factorial behind it, because we have one of those ready to cancel out in the numerator on the other side. All right, let me make sure I got all that good. Yeah, I think so. Okay, clean that up, find your limit, and see what we think. Because this one should make you think a little bit. and then see what you think your interval would be. Like on what interval would this converge for sure? All right, let's see what we're getting here. So I broke it down. The x to the 2n plus 3 is x to the 2n times x cubed, x to the 2n times x to the first for the 2n plus 1, just so we understood where all that came from. So the n factorials, hopefully we definitely understood that those canceled. Then you would have had an x to the 2n in the numerator and in your denominator. And then we would have had an x cubed in the numerator and x to the first in your denominator. So our final simplified version, before you would have found your limit, hopefully was this. Let me get to that point. And then now what we want to figure out is what limit do we have as your n's? And remember, this is just your n's getting bigger and bigger and bigger. What do we think for that limit? Lily? Good. Has to be a 0, right? If you think about exponents, if I put an n in this numerator, doesn't the n have to have an exponent of 0 because it wasn't there to begin with? So the bigger n degree is in your denominator. So that has a limit of 0. Aren't we looking for this to be less than a 1? So does it matter what x value we are dealing with if we're going to get a 0 no matter what? No. So isn't this always going to be less than a 1? So when that happens, what this is going to tell you is that this converges on an interval from a negative infinity to infinity. So if you remember yesterday, it only converged in that little window, negative 1 to 1. We can clone the graph in that interval. What this is going to do is clone whatever its function is everywhere. You can basically reproduce an entire graph from this. All right, and there's certain ones like sine, cosine, exponentials that will do that we're going to get into here over the next few days. All right, so that's what that means with the infinity over the infinity. Go to number 11 next. So go through that and see what we think for this one. And then the nice thing about that, though, is you don't have any endpoints to worry about. Another one at the end they should think about a little bit, see if you can kind of process what this now means. And even if you think you're right, it's probably not completely right. All right, is that what we get? X times n plus a 1 over a 1. All right, so then we're going to go ahead and figure out what is that limit as the n goes to infinity. What do we think for this one? So as your n's get bigger and bigger and bigger and bigger and bigger, what would this limit be? Good. So this would have a limit of infinity. Right, you could say you could throw some absolute values around those, I suppose. So up here, our interval was everywhere. Because it didn't matter what x was, the limit was always going to be a 0 regardless of your x coordinate. So now it's saying that as n goes to infinity, this will be infinity. What do we think for our interval here? What's that? Okay, so no interval, and that's where we want to be just a little bit careful. Because up here, so Brian's right. This basically means it doesn't really converge anywhere. with one exception. So up here, it doesn't matter, right? No matter what I let right here, I'm going to get a 0. But if I come down here, what if x is a 0? Even if this is growing unbounded as n goes to infinity, if x is a 0 here, anything times a 0 is going to be a 0, correct? So we do have a very, very small little window. We basically only converge to one value, or we'll say at one value, at x equals 0. So they're all going to go through this value, but after that, they're just going to kind of go off and do their own thing. Okay? All right, last one. This is a nice one. No tricks here. So to kind of wrap all of these up, make sure we have a good handle on all of these. So when we get to these on test, whatever we have, or 2 weeks from the day, because you will absolutely get one of these questions on the AP test. Wrap up number 10, see if we can get through one of these in its entirety. I'll give you a couple minutes here. If you get stuck, unsure, I'm doing it, you can kind of take a peek, just make sure everything's matching up. Try not to screw up. The endpoints will make you think a little too, right? But hopefully we got to the 0 and the 4, okay? Then plug those in. You're going to get some weird stuff. You want to clean that up. Use some algebra, clean it up, make it the most simplified little series that you can create so that it's easier to identify if it's converging or diverging. It would. So it's up. It just kind of gets ugly with the inequality. So I had that initially here. Yeah, and then since we're just going to do the absolute value of it, I just turn that to positive right away. And then it makes this over here a little easier to handle. You don't have all the weird signs going on in there and the flipping of the inequality, all that silly stuff. All right, hopefully the 4, the x equals 4 was the nice one. That should have played out pretty similar to some that we've done before. At x equals 4, you would get this initially. These are going to cancel. We get the little negative 1 to the n plus a 1 over an n. So it's an alternating. And then this is the harmonic series. So do we all get 4 to converge? Good. So 4 should converge. It's conditional. In all honesty, you could actually say converges. All we're looking for is does it converge or not. So actually, really, really good chance you get to do this on the free response portion of the AP test. If you just put converges, alternating series theorem, that's totally fine. That's enough of a justification. All we want to know is, do we need to close this interval off or not? And we do, because it converges. So if you want to be more specific, even better. That's something you need to know, but we could just put that. All right, this one, though, a little trickier. Negative 1 to the n plus a 1. And then a negative 2 to the n over 2 to the n would give us a negative 1 to the n, and then all that over an n. So, little algebra test here. If I now multiply these together, we said we have to add those, correct? So those added together should give you a 2n plus a 1 over n. So now the question is, if that alternates, it's the same as number 4, right? Alternating harmonic. If it doesn't, then it is the harmonic. And the first time we've seen this 2n plus 1. So if you're not sure, just throw in some numbers. If I plug in a 1, won't I get a negative 1 to the third power, so negative 1 over n? If I let my n then be the next integer of 2, wouldn't I get a negative 1 to the fifth power? So I still get a negative 1 over n. If your n is a 3, now I'm a negative 1 to the seventh. Don't I always get a negative 1 over n? So is it an alternating one? No, it looks like maybe it is. First time we've really seen this little guy here. But that's always going to be an odd power, so you're always going to get a negative 1 over n. So this should do what? Diverge. Pen is, there we go, a little better. That diverges, and because, why? That's still the harmonic series. Don't freak out that it's a negative one versus a positive one. That would just be diverging in the negative sum, right? Negative direction, so that's still the harmonic series, okay? So the 4 we close. Here's that. Let's make sure we understand the radius here. We were centered in this one at what? 2. And we go to 4 and 0, so our radius is 2. All right. All right, so that's that. Okay, real quick, because I wanted to spend 2 days on these because this is the second day and the second day is short. So I don't know if it's quite short enough, but go to that next, the 9.3 continue. Is that your next page? Yours? Okay. All right, so 9.3 continue. We just got done talking about power series, how it's an infinite polynomial, and now let's talk about differentiation and integration. So derivatives and integrals of these. So to start with, recall that 1 plus x squared plus x cubed is really this 1 over 1 minus x, and it stems from the sum of a geometric series. So our first term in this was a 1, so that's why we put a 1 on top. 1 minus our ratio. Notice how we're multiplying by an x over and over and over again. So we just use that formula with these first terms and that ratio. All right. So what I'm asking you to do is find a series that would represent 1 over 1 minus x quantity squared. So here's how you're going to set this up. Underneath this, we're going to recopy what I have written for you. So just rewrite that out. Then a big note to make, either on your paper or in your head, when it says find a series series, I think I mentioned it before, means every single term. The only way to do that is with the general term. So what we are ultimately looking for, we don't necessarily need any of these. We're going to get them. The answer to this is going to be the series that gives us this, the general term for that. All right, so come off to the side here. And what we're going to do is take the derivative of this. All right, so most of us do the quotient rules. Let's go ahead and do the quotient rule here. Your denominator multiplied by the derivative of the top, which is a 0, minus the top, and then the derivative of your denominator would be a -1, and then all over your denominator squared. Then before we do anything else on the right-hand side, simplify what we just found there. So these would cancel because of that 0. Don't we end up with a +1 in the numerator, and then the quantity 1 minus x squared in our denominator, which is what we are trying to find right here. So did we just create that by taking the derivative of the one that we knew? Well, if these are in fact equivalent to each other, which we said they are, then whatever I do to one side, I should be able to do to the other side. So on the other side, if I took the derivative of the left, I'm going to take the derivative of the right. So the 1 would go away. The derivative of x would be a 1. The derivative of x squared is 2x, 3x squared, so on and so forth. However, what we ultimately want is the general term here. That's the answer if I want you to write the series. So write down what you think that general term would be, so that we would get 1, then a 2x, and then a 3x squared, so on and so forth. Don't overthink it. It's really easy. Because you could look for the pattern. If you're going to try to do it by patterns, that'll keep you busy for a while in some of these. But if I just took the derivative of each of these, couldn't I just take the derivative of this guy and multiply by n, and then don't we subtract 1 from that power? That simply is your series. That is the series that's going to produce this. All right, remember, this here is equivalent to that general term. So whatever I do to this guy, I just do to the other one, and those are going to be equivalent to each other. All right, easy enough. All right, next one, same idea. That's really what this is just saying. Just term by term differentiation, very complicated math speak right there. Even if we had time, I don't necessarily spend a ton of time on that. So go to number 2. A little more obvious what we're supposed to do here. I'm giving you that this is 1 over 1 plus x. Now this is alternating, so the reason we have a plus x here is because we're multiplying by a negative x each time. And then we have a negative x to the nth power. So find a power series that would represent the natural log of x plus 1. So hopefully this is a little more obvious. What would I need to do to the one that we have to work with to create a natural log? We'd have to do what to this guy? Antiderivative. So if I throw an integral in front of this, isn't the antiderivative of that just the natural log of 1 plus x? So what that simply then means is just go term by term by term by term by term and do the antiderivative of those. But what we ultimately want, this should be a 5, is that general term. Because again, I'm looking for the series, and the series means I want all of them. And the only way we do that is with the general term. with this one, be a little bit more careful, because hopefully at least you're thinking, all right, well, let's just do the antiderivative of this and get a negative x to the n plus a 1 over an n plus a 1. Is that our thought? All right. However, think about here's what I would strongly suggest with any of these. I think I talked about this one other time. When we have the negative as part of the power, what I would strongly suggest is pulling that thing out and dealing with the alternating term all by itself, that little negative 1 to the n or the negative 1 to the n plus a 1. All right? Just because if I now come down to here and we start trying to actually plug in some values, shouldn't I get a positive x initially right here? And if I throw in a 0 right now, I'm going to get a negative x to the first power, and it's going to give me this negative x. So what I would strongly recommend then is, with this guy here, leave that thing alone. So we're going to do a negative 1 to the n out in front. And then now I would just do that x to the n, and then divide by that n plus a 1. All right, now, still see if this is going to work. You still got to be just a little bit careful. If I start at 0, won't I get a 1 in my numerator? That's not the first term that we wanted here. If I start at a 1, I'm going to get a negative 1 times x, also not my first term. So what we got to do is play a little bit of a game. That's why it's nicer to kind of pull that out. So let's start at 0, and as long as I then do, what do I do? What did I start at? Yeah, an n, and then we're going to do this as an n plus a 1. I should have had that anyway, right? Did I forget to put that in there? Yeah, then we're good. Then n is a 0, you're going to get x to the first over 1. If your n is a 1, you get x squared over a 2. All right, so on and so forth. All right, so that's the series that would give us this. If I were to graph this, now we're going to graph a bunch of those terms, everything should work out okay. All right, real quick. Sorry, we're going to continue to press through here for these last few. So go to the next one. It says find a power series that represents this. So first, write down these general terms. So again, this is first term divided by 1 minus your ratio. So our first term had to be 1. And if I ended up, instead of 1 minus r, I end up with 1 plus x squared, what that means is my ratio had to have been a negative x squared. And then that's why I would get the 1 plus x squared. So if the first term is a 1, just start multiplying by a negative x squared over and over again. Then we're going to alternate. So let's do the little negative 1 isolated, left alone. Try not to put that inside with the other part. And then we're just taking the x squared to the nth power. You can write that totally fine, 100% correct. But in general, you're probably going to get it written then just power to a power we can multiply as x to the 2n. Also, now that I look at this, I just looked at my notes here. Add a word here, otherwise this doesn't make any sense. So it's asking, what would the new integrated power series give you? So get a little question now. If I ask you to find the antiderivative of this, Brian said a minute ago we got a natural log. Anybody remember what this guy was? The 1 over 1 plus u squared, if I put it in terms of u. Good, that's the inverse tangent. So if I now start doing this, antiderivatives everywhere, all we then have to do to come up with the series, the alternating part we leave alone, and then you just do the antiderivative of the general term like we normally do. And then this series here, as our n is a 0, would produce the inverse tangent. And then if the bell rings, hang on just a second, because I went through all of this before class put it in. Here are those terms we just wrote out. So then just kind of look. That's the series. Watch the inverse tangent come in. And it basically models that. And the more I add to the terms, the more it's going to produce the inverse tangent graph over and over and over again. All right, we're done. Go. Close this. right, thanks, Aaron. All right, we'll see you guys.